Welcome to the Cosmic Savannah with Dr. Jacinta Dalhays
and Dr. Daniel Kahneman. Each episode, we'll be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Hi, welcome to episode 49.
Episode 49, are we going to do something special for episode 50? A half century.
Oh yeah, goodness, that happened fast.
Yeah, and now we've put pressure on ourselves to do something special.
Oh no. We should have planned this. We also have something special for you this week. Today we will be talking to Dr. Elizabeth Naluminsa about her work with the SALT telescope and a particular spectrograph and a particular mode on that spectrograph called the Fabry-Perot interferometry mode. So we will explain everything about what that is, and as will Liz. But this particular episode is to celebrate something special, right, Dad?
Yeah, the International Astronomical Union is running a Women in Astronomy Month. Is it a month?
I think it's not quite a month. It's between the 11th of February, which is the International Day of Women and Girls in Science, and the 8th of March, which is the International Women's Day.
Yeah, and basically that'll be focusing on celebrating women in astronomy and in science.
Yeah, Women and Girls in Astronomy, and that's run by the IAU, so the International Astronomical Union's Office for Astronomy Outreach. So that's OAO, Office of Astronomy Outreach.
Yeah, so and as part of that, you spoke to Liz.
Yeah, so I spoke to Liz as part of this Women and Girls in Astronomy project. It's kind of an international thing where there's loads of different events and initiatives involved with this idea all over the world. And you can go onto the website, and we'll put a link on our show notes page where you can go and find out about all of the activities going on hopefully there'll be something wherever you are, but there's a lot of virtual events going on that you can join in. For kids, there's a draw an astronomer competition, and yeah, lots of other things. There's a YouTube channel where you can go and see videos from women in astronomy, and lots of stuff on social media, so check that out.
And our podcast, hopefully.
Yeah, and this podcast, hopefully, we must remember to register it officially. This episode will come out during that time. Yeah, so that hopefully we can be part of it and be on their calendar.
And speaking of women in astronomy, of which you are one of, you have some news?
Yes. So this week, or last week rather, from the 1st of February, I have started a new position. I'm now a lecturer of astronomy at the University of Cape Town Astronomy Department. So I will be teaching third year extragalactic astrophysics. So if you are currently studying astronomy and you're going into third year, or you will be going into third year, I will probably be your lecturer. No pressure, but yeah, so I've only lectured twice before, so I don't have a lot of experience, but I'm a junior lecturer and it's an opportunity to get more experience, and I found that I really enjoy it. The students are really great, so yeah, looking forward to sharing my expertise with the next generation.
And you obviously have plenty of experience in communicating science, so I'm sure it'll come naturally.
Oh, well, thank you. Hopefully it does. But, my course is just in one semester, and for the rest of the time I'm continuing my research as normal. So I'll still be continuing my work into galaxy evolution, trying to study how galaxies change and evolve over the history of the universe, how the supermassive black holes inside galaxies are kind of churning up the gas, heating it up, blowing it out, how much gas there is, how much stars they're forming, all of this kind of stuff. So, yeah. Continue on with my research.
At some point we'll have to have you back on the podcast as a guest.
Yes, maybe when the next paper comes out.
People will start thinking we're biased.
We are.
Fair enough. Okay, touche.
Okay, that's enough about me. What have you been up to, Dan?
We spoke about Atlas in the last episode with Nick, and the telescope was just launched. We had dignitaries there, the Parliamentary Portfolio Committee up there, and very exciting international release. NASA put out a release, the University of Hawaii put out a release, and that triggered huge amount of media interest. So I did a lot of radio interviews. There was a lot of media. I'm actually recording a TV interview this afternoon. So that's taken up a lot of my last week, but very exciting. And even since we spoke to Nick and since the press release came out, Atlas has found another asteroid, near-Earth asteroid, which passed just 2 lunar distances from Earth. So that's getting quite close, but it was only 20 meters across, so less concerning. And then it's also discovered, I think, at last count, over 60 other transients. So, Atlas is looking at the night sky every night for anything that moves or changes, and therefore it actually finds other things other than just asteroids. It finds supernova and anything that changes in brightness or position over time. And supernova definitely change in brightness quite rapidly. So it's detecting these other objects too, and then passing them on to specialist telescopes who can follow them up. So it's been a very, very busy telescope and operating perfectly.
60 transients, gosh, that's remarkable.
Yes, well, I think that as more and more of these telescopes are coming online, we're just going to get more and more and more of such objects. And Atlas isn't even particularly deep looking, so it's looking at a large patch of the sky relatively deeply. But once you get even bigger telescopes doing these sort of nightly surveys, I think we're going to be completely inundated with transients.
Yeah, the Vera Rubin Observatory with the LSST survey that we keep mentioning. That'll be, next level.
Legacy survey of space and time.
Very good.
Yes.
I think that's right.
Oh, no. We'll Google it and correct ourselves at the end again.
Finally. Yeah, that's a hard one to remember. Probably our listeners will know it by now, even if we keep forgetting.
But back to today's episode, you spoke to Liz.
Yes.
Who is something of a pioneer in women in astronomy.
Yes. So Liz is from Uganda, and she is, as far as we know, the first Ugandan woman to get a PhD in astronomy. And if you also remember episode 10, we spoke to Priscilla Muhechi. She's now finished her PhD, and she becomes the first woman to get a PhD in astronomy from a Ugandan institute. So Liz became the first woman, but she got her PhD from South Africa, and Priscilla has just graduated from Uganda. So that's really exciting. Congratulations to both of those women, and hopefully the first of many.
Absolutely.
Yeah. And Liz is working in Cape Town now. She works with your institute, Dan, at the SAAO, the South African Astronomical Observatory, with the SALT telescope, which is the Southern African Large Telescope, biggest optical telescope in the Southern Hemisphere. And it has several different kind of instruments on it. So the light bounces off the primary mirror and ultimately gets collected into these different instruments, whichever one the observer wants to use. And some of those instruments are spectrographs. So Liz and I try and explain kind of what a spectrum is, but maybe we should go through it beforehand, Dan.
Yeah, so I think that the thing to remember about telescopes is the telescope itself, as we would picture it or think of it, is essentially a light bucket. So it's a big mirror in most cases, which is collecting as many photons as it can. The bigger it is, the bigger its aperture, the more photons it can collect, which means the more faint the object that it can identify and observe. But collecting the light obviously is just the first step. Then you need to do something with it. The obvious thing is to focus it, and then you can take an image or something. But there's a lot more you can do with that light. The photons, which have traveled across the universe, have an incredible amount of information in them. They have color, so they have different wavelengths, they have polarization, they have all sorts of things which have been embedded into their characteristics, which, given the correct instruments, we can weed out of them and try and learn about where they came from and what environment they came from, what object they came from. And SALT obviously has different instruments with different specialities to try and work out where these photons are coming from. And, what you can work out how fast they're moving, how far away they are, all sorts of things like that, just by looking at the light in much more detail.
Yeah, exactly. So then, as you said, the light bucket, which is the SALT telescope, the mirror, collects the light, and we have to decide what to do with the light once we've got it. And one thing we can do is to split the light up into its different wavelengths or its different colors. If it's in the optical, we can see different wavelengths as different colors with our eyes. But the spectrographs do this so that it splits it up into very tiny wavelength ranges or color ranges. So you can think of it sort of like splitting it up into light blue, then teal, then aqua, then dark blue, then navy, kind of like that, but in really small increments. Sort of like that. I just chose my favorite color, which is blue.
Yeah, I mean, but like teal and aqua, are those colors? That's not what I learned at school.
No, I mean, but you know what I mean, right? you get the point.
As far as I'm concerned, there's 7 colors.
Do you mean 6?
Red, orange, yellow, green, blue, indigo, and violet. The colors of the rainbow.
But indigo's not a real color.
Isn't it?
Indigo's not a real color. No, don't you know the story? Isaac Newton was apparently quite religious, and 6 was like the devil's number or something, or 7 is a good number. I can't remember. And so he added an extra color in.
I did not know that.
I'm going to Google. Who invented the colors of the rainbow?
Who invented the colors of the rainbow?
Oh, it was
Science
Isaac
did.
Newton. I was right. Indigo's
Oh, right,
not
well,
a thing.
I didn't know that. Okay, well,
You're
tell
an
that to my daughter
astronomer.
who has 2 different purple crowns.
I mean, but there's many different wavelengths and it's a continuum, right? So
Yes.
anyway, the point of splitting up your light into these different little segments, I guess, is you can study a couple of different things. One thing is you can see the emission line from particular elements or chemicals or molecules in space. So it's a way of kind of studying the chemical composition of whatever you're looking at. So for example, you might be able to detect oxygen in the atmosphere of an exoplanet. I mean, I'm, wishful thinking here, but
For example.
for example, you might be able to detect hydrogen or nitrogen or all of these different chemicals, carbon in stars, in the atmospheres of stars, or in the interstellar gas of galaxies. So it gives you more information about whatever it is that you're looking at. And it can also give you information on how fast that chemical, that molecule, that atom is moving. So distances are really hard to figure out in space, but velocities are not so hard. So it actually really helps you you can look at the spectral line of the molecule or the atom or the chemical that you're interested in, and you know what wavelength you're supposed to be seeing that light at. And if you see it at a wavelength that's slightly longer or slightly shorter than what you expect, then that's telling you that that gas or that atom or whatever it is either moving towards you or away from you in space. And then this is how you can understand the movement or the velocity of the gas or the chemical. And then you can tell perhaps that you have a galaxy that's rotating in a certain direction. You have maybe some gas that's been blown off the outer layers of a star in a certain direction. So you can get a lot of different information from these spectra.
Yeah, for sure. I mean, photons have embedded in them like the entire story of their past, where they started, where they've been. And it's our little challenge and hobby, job, to work all that out and solve that mystery.
To reconstruct the past, almost.
Exactly. Wasn't it fun?
Aww, that's so nice. We're historians. Who knew?
I love the whole idea of the photon. You look at an individual photon, and in it is like, obviously, there's a sad end in that it ended either in your instrument or in your eye, but it could have been traveling for 13 billion years, and it's traveled through different, gravity wells and clouds of gas and everything else, and all the while picked up information, which then comes and lands in our instrument somewhere in Sutherland and then dies.
You should be a poet.
Oh, thanks.
But anyway, getting back on track.
Yes.
So SALT has various spectrographs. One of them is the RSS, right?
Yes, the Robert Stobie Spectrograph.
Okay, so it's called the RSS spectrograph. And there are different modes that you can use this in, as Liz will tell us. And one of these is called the Fabry-Perot mode. This particular mode has been offline for a while, so observers haven't been able to use it. But now it's being kind of recommissioned thanks to the team that Liz works as part of. And Liz's particular role within this is to write some software to calibrate the Fabry-Perot mode so that it's working properly, and also to write the software that helps the observers use the data that's coming from this particular mode. So very advanced stuff, very impressive stuff. And perhaps we should let Liz explain the rest. Oh, we wanted to also talk about what NASP is, right?
Liz is one of the graduates of the NASP program. I actually went through the NASP program myself too. And the NASP program is the National Astrophysics and Space Science Program, which is run here in South Africa. And it was established, I think, 25 years ago now, initially with its node in Cape Town at the University of Cape Town, but now it has 2 additional nodes where students can study in Potchefstroom in the center of the country near Joburg, and in KZN in KwaZulu-Natal near Durban. So the idea with the NASP program is there are honors and masters courses where students can come from around South Africa and Africa, and they can get exposure to a wide number of subject matter, things related to space science and astronomy. They get lectures on them, and then from that they can choose their master's project and PhD projects. So it's a way of bringing together the community of astronomy into a few places where we can get the best astronomers and the best lecturers all in one place, rather than trying to spread it out over all of the universities in the country. And then, as I said, it serves the rest of Africa too. So we've had a lot of students over the last 20 years coming from other African countries, of which Liz is one of them. And it's wonderful to see another graduate succeeding, and just an excellent program NASP has been. I'm not sure what the last count in terms of the number of PhD astronomers that have come out of NASP, but it's a lot.
Yeah, so definitely a lot of people sing its praises, particularly all of its graduates. It's an amazing program. And as we said, Liz is one of the graduates from the NASP program. Let's hear what she has to say. With us now is Dr Elizabeth Naluminsa from the South African Astronomical Observatory. Welcome, Liz.
Thank you. Thank you, Jacinta. I'm glad to be here.
Thank you for joining us. Can you tell us a little bit about who you are, where you're from, and what got you into astronomy?
Well, as I said, I'm Elizabeth Naluminsa. I come from Uganda. I'm an astronomer. I like to say that I'm a Ugandan and an astronomer. So I came from Uganda in 2010 to 2011 actually, to pursue further studies. But before that, I had done a Bachelor of Science at Mbarara University of Science and Technology, majoring in physics, and I had developed interest in astronomy way before that, during my high school years. So what got me interested, I think specifically, was the moon story, Apollo landing.
Yeah.
I read about it as a kid from textbooks, and I thought that was really cool, that there was stuff out there that was real, It wasn't just out there and unreachable. So that got me quite interested. So when I finished high school, unfortunately, there was no course for astronomy in Uganda. But I was so lucky that when I went to university, the Department of Physics had started incorporating bits of astronomy in the curriculum. So we'll do a unit here and a unit there about astronomy, and it was really good. So I picked interest, and then I applied to join the National Astrophysics and Space Science program in South Africa, for which I was recommended by the department, and it turned out really good. I was so grateful to receive that kind of mentorship and support from my department back home. And then when I came to South Africa, I did my honors degree, master's, and PhD in astronomy. And here we are.
Wow, what a journey.
Yeah.
So what university did you do your honors and masters and PhD at?
I did that at University of Cape Town in South Africa.
And how was that experience? That must have been quite a big change to come from Uganda to Cape Town, and a different country, and study something completely different.
It was quite interesting. There was a massive culture shock to begin with. And also the education system was quite different. But I think I caught up soon enough, because there were other Ugandans that had done the program before. as well as other Ugandans and East Africans in the university. And I think I like meeting new people, so I guess it was fun altogether. It was fun altogether.
I'm glad you enjoyed the experience and that you persevered. So, is there a large astronomy scene in Uganda? And I actually heard that you were the first or one of the first women to graduate with a PhD in astronomy from Uganda. Is that true?
I don't know, because I haven't run a study in the entire world to find out what Ugandan women are doing everywhere in the world.
Fair enough, fair enough.
But astronomy is a relatively new field of study in Uganda, but the efforts to develop it have been ongoing for about 10 years or more, and I think they were begun by mainly 2 or 3 people: Professor Anguma in Muni University in Uganda, Professor Jurwa in Bara University, and Professor Dujanga in Makerere University. So especially for me, the influences I had were Professor Anguma and Professor Jurwa. Back then, there was effort to introduce it into the curriculum, at least at university, as part of physics. And a course that was dedicated to astronomy was not yet there, but they introduced elements of astronomy into the physics curriculum, introduction to astrophysics, and then there would be general public talks where we would interact with the information that we find. Mostly the source of information for us was the internet back then, because as I said, it wasn't a major part of the curriculum. There were no textbooks yet that the government had provided for the curriculum and what. But right now, there are efforts paying off. So I do not know how many women that are Ugandan that are out there that are astronomers. I'm still looking for them, like it's an active search, literally.
Yeah.
I want to find a community to find them wherever they're hiding. But I did get my PhD in 2019, so glad, and recently was joined by Dr. Muhechi, who actually was the first to get hers from a Ugandan university, not like just a PhD in astronomy.
Yeah, a PhD in astronomy from Ugandan University, right?
From Ugandan
Yeah.
University. So yeah, there's a growing community now. Like, for example, there's a community that is growing at different universities. At Busitama University, there's a community that is being developed by Dr. Amabayo, who is the head of the physics department there. There's an astronomy community being developed at Chambogo University, also in Uganda, by Dr. Abedi Gamba, who is also an astronomer, and Dr. Nsamba, who is also an astronomer. Then there's the community that is still being developed by Professor Jurwa, which includes Dr. Mutabazi, who is also an astronomer, who many of these people, if not most, they came from the NASP, they're products of the NASP. So there is a community that is growing, and the government is also picking interest in this with its connections to telecommunications and cutting-edge technology. So I'm of the view that it's a growing community, and soon it will be even more and more vibrant with the government getting involved. And the IAU has always been supportive of astronomy in Uganda. It's been a very good relationship we've had with the IAU.
Oh, that's fantastic. So that's the International Astronomical Union.
Yeah, there's an organization back home, a private organization that is driving space technology, and it's also headed by a NASP. So NASP has done things for Uganda.
Oh, wow. So NASP is the National Astronomy and Space Science Program that's run here in South Africa. All right, so it sounds like the community in Uganda is growing, and that's really fantastic. And also congratulations to you on your achievements. So you finished your PhD in astronomy here in South Africa, and now you are working for the South African Astronomical Observatory. Can you tell us a bit about what your role is now?
So right now I am a postdoctoral fellow on the Southern African Large Telescope, specifically working under the operations team. And my role is actually software based, which is quite interesting that my PhD was on extragalactic astronomy research, multi-wavelength extragalactic astronomy, where I looked at star formation in nearby galaxies. But I did quite a lot of software development during my master's and my PhD, which got me really interested in programming.
All right.
So right now my role is basically writing software and doing very fun stuff like observing on SALT.
Oh, cool. Oh, cool. So you actually get to observe with SALT.
Well, actually, As part of my role, because my work actually, what I didn't elaborate on is to help in commissioning of the Fabry-Perot interferometer on SALT and to give support to observers and PIs for the schedule, expected to have an understanding of how the telescope works and how the different instruments communicate with each other and with the telescope. So yes, I get to learn some things about observing, and last week was actually my first solo run on the telescope observing. Yes.
Cool! You did it all by yourself.
I was there with the operator, and I also had a backup SA, a backup SALT astronomer, those that are hired specifically for that role. Yeah, but it was pretty fun. And for my first night, actually, we observed a near-Earth object, an asteroid going by.
Oh,
It was
cool.
super cool.
Oh, we
Yeah.
chatted last episode with Nick Erasmus, who works on the near-Earth asteroids, and he was telling us about some of these objects. So that's so cool. You actually got to see one with SALT, which is a massive
Yes,
telescope.
on my first night with
On your
SALT.
first night. What an epic first night. That's amazing.
It was so amazing.
Was it scary, or did you feel really confident, or how did it feel?
Well, it was a mixture of feelings. First of all, watching the asteroid like just go across the screen, it was surreal.
Wow.
Of course, I was a bit anxious because it's Q observing. Time is strictly limited, and many of these objects, like for example, the near Earth object that we observed, it was very limited in time, and it was a trigger observation. So you have to get it when you can get it, you know. So there was a bit of anxiety. The nerves were there because it was my first night, you know.
Yeah.
And there's, very important observation
Yep.
coming up. All observations are important, but some observations are very important.
Because they can't be repeated.
Yes. So the excitement and the nerves and, wanting to do it right because you want to give to the community the best you can give.
Yeah, awesome. On my first night of observing by myself, I was at the Parkes Radio Telescope in Australia, and suddenly all the alarms went off. And I just freaked out because I thought I had broken the telescope. It turns out the power had just flicked off and on again, and you just have to reset the alarms. But oh my goodness, I freaked out. I'm sure I still have bad dreams about that now. Oh, but anyway, well done. What an
I
exciting...
know about that. I was worried about breaking the telescope every minute of that night. But I had been trained several times by the different SALT astronomers, and they were very supportive. No, don't worry, you're not going to break anything. You know what you're doing.
Good. Okay, so you got through that, and so now you have a better understanding of how observing with SALT works and how all the instruments talk together. Because of course you've got the big mirror,
Yes.
Which collects all of the light. But then the light is focused and sent into these various different instruments, which collect the light and process the light in different ways. And I think you said so you work with one of those instruments in particular, right?
Okay, so to begin with, SALT is the largest optical telescope in the southern hemisphere, and it is made of 91 hexagonal segments which are reflecting surfaces. It's quite a massive piece of engineering, and it has several instruments that work with it. Spectrographs, the famous Robert Stobie Spectrograph, the Echelle spectrograph, the high-resolution spectrograph. But my specific instrument is actually a subsystem of the Robert Stobie spectrograph, in the sense that it is an observing mode. So on the Robert Stobie spectrograph, you can either propose to observe using the long slit spectroscopy mode or the multi-object spectroscopy, or you can also observe with the Fabry-Perot mode. Now, there's also other instruments that are coming on board and lots of cool stuff that's happening over there, cutting edge of technology. I am having the time of my life. But so my specific role is with the Fabry-Perot observing mode, which gives us the capabilities for 3D spectroscopy, that is wide-angled 3D spectroscopy.
So much amazing stuff and quite a bit of technical things there. So let's just break that down for the listeners and also for myself, because I don't really do optical, and so I'm not really that familiar with spectroscopes. Spectroscopes or spectrometers?
I know, right? What exactly is that
What's
thing
it?
called?
What is it?
Spectrograph.
Spectrograph.
Sometimes people call them spectrometers. I'm like, no, a spectrometer is found in the lab. But then
Oh,
another one will tell you, no, it's the exact same thing. But I'm like, no, the other one is a mass spectrometer. Oh,
okay,
Lord.
okay, all right. So I'm corrected. So
Yeah.
spectrograph. Right. So there's all of these different spectrographs on Sol, and what that means is that the light can be split into different wavelengths, and so that we can study the particular emission lines of different gases and chemicals and metals and things in space, inside galaxies and stars and other things. But there are different types, different ways you can do spectrometry and different types of spectrographs. Is that correct? And one of the ones is Fabry-Perot. Is that right?
Yes. So to be clear, there are two currently, right now as we speak, there are two spectrographs. Okay? In the future, there will be a lot of news, you'll get it. But currently, there are two spectrographs. So there's the Robert Stobie Spectrograph and the Eshel Spectrograph, which is called the High-Resolution Spectrograph.
Right.
Okay? Now, the High-Resolution Spectrograph uses fiber feed.
Okay.
Okay? But it's not IFU. Then the RSS has different modes of spectroscopy.
The RSS is the.
Robert Stobie Spectrograph.
Oh, is that what RSS stands for?
Yes, the
Oh,
famous
I've always
Robert
wondered.
Stobie.
Okay. Okay, so we've got the RSS spectrograph.
Yes, and on the RSS spectrograph, you can choose to observe using either the long slit spectroscopy mode or the multi-object spectroscopy mode. Different modes are being worked on to give RSS even more versatility. But there's also another mode which is called the Fabry-Perot imaging mode.
Okay, so we've got two spectrographs currently on SALT. One of them is called the RSS, and it has different modes. And one of those modes is the Fabry-Perot. And that's what you're going to be talking about, right? That's what you work on.
Yes.
All right, we got there.
Yes.
Cool. So tell us about the Fabry-Perot. What is it and what are you doing
Cool.
with it?
So I'll begin with what spectroscopy is generally. Usually when an image of astronomy is seen by the public, they admire how beautiful it looks because
definitely.
it is beautiful.
Yeah.
Let's be honest, it's quite beautiful. But from those images, we get to learn a lot about the distribution of material in the different objects we study. For example, the distribution of gas, the amount of gas in different parts of galaxies. From images, we get to study the distribution, for example, distribution of gas, distribution of stars in galaxies. We see the spiral arms, and there's a lot of information that we learn from the images because it's not just an image, it's actually a collection of data points.
It's like a map, right?
Exactly.
Yeah.
So the other mode of astronomy, if I may say, that the public doesn't usually, the other mode of astronomy that the public usually doesn't get to interact with is the spectroscopy. So spectroscopy is what we actually use to find out what are the chemical elements in these images that we are looking at. So we get to see the picture and then we want to know what is the composition of this picture. So spectroscopy helps us to see the why behind the what. And also from spectroscopy, we get to look at the motions of the gas and stars in the galaxies. We get to learn how is the gas rotating, for example, around the center of the galaxy, or are there gas inflows or outflows out of the galaxy? How much of this element do we have? What are the edges of the different stars that we are looking at? A lot of this information, we get it from spectroscopy by studying the abundances in these objects. Now, it so happens that imaging and spectroscopy are traditionally done separately, but there's a technique called 3D optical spectroscopy, which combines both the imaging and the spectroscopy, and it is called imaging spectroscopy.
Well, that makes sense. That's a good name for it, imaging spectroscopy. Okay, so usually with spectroscopy, you don't get a picture, like a map on the sky. But what you're saying is that with imaging spectroscopy, you do.
Yes, you get both, the best of both.
Fantastic. Okay, so tell us more about that and how the Fabry-Perot relates to that.
Good. So the technique called imaging spectroscopy is also called 3D spectroscopy because you get to see both an image as well as the spectrum. Now, the Fabry-Perot imaging mode is actually one of the ways that we achieve 3D spectroscopy. It is made of 2 glass plates. So the Fabry-Perot imaging mode is one of the ways we can achieve 3D spectroscopy. It is made of 2 glass plates, which are made so that only a specific wavelength of light can be transmitted through those glass plates. So when the light is incident on one face of the glass plate, it is reflected multiple times between the 2 plates, and then it is transmitted through the second plate and focused onto a detector. So we get to catch an image this way, but then we can scan across different wavelengths by changing either the separation of the plates or the air pressure between the plates, so that we can get several images at different wavelengths. And these images are very narrowband images. In the end, what you get is a data cube. And by data cube, I mean you get 3 dimensions. The XY, which would be your right ascension and declination, and then the Z, which is the spectral axis.
Okay, so the spectral axis is like different wavelengths.
Yes, different wavelengths. So you get several images at several wavelengths. But if you were to extract 1 pixel from this cube, you'd get a spectrum. So you literally have a spectrum at every point of your image. In other words, you can get extra information at every point in your image.
This is really exciting, and I'm not sure if listeners are aware of this, because not even I was aware of this until recently, like in the last, decade or so, that this has been possible to get 3-dimensional spectral images.
Actually, 3D spectroscopy has been around for decades.
Oh, really?
Yeah. It started with Fabry-Perot interferometers, but the complexity made it not very appealing.
Ah.
And there has been 3D spectroscopy on La Palma, 3D spectroscopy in, I think it's SAO in Russia. There's been 3D spectroscopy. It's been quite all over the place, actually. It's just that...
Oh, I didn't realize it was that prolific.
Yeah. In the last decade or so, fibers have now become more commonplace because the data that comes out of the fiber it can much more easily be reduced, although it gives you a smaller field of view, but it gives you an instantaneous cube, and you're able to reduce it the way you would reduce the traditional long slit spectroscopy.
Reducing is like processing the data after you've collected it.
Yes, processing the data.
Yeah.
I'm sorry, lingo.
Oh, astronomy's full of it. Okay, so you work with the Fabry-Perot on SALT, which is these 2 plates, and by moving the plates closer together or further apart or changing air pressure, you get essentially a 3D image which has spectral information in there, which gives you lots of great information about the chemicals in the galaxies and the movements of the gas and everything. All right, that's fantastic. So what is your role related to this?
So my role in this is to help recommission the interferometer. So observers and perhaps members of the public would have noticed that over a while there hasn't been work done using the Fabry-Perot imaging mode, and that's because the plates had to be refurbished and a lot of improvements had to be done to them. So now we are in the process of getting a new system with new etalons. When I say etalons, I mean that combination of the parallel glass plates. So my role is to help to write new calibration software to help to deal with the complex data that comes out of it. So when you do spectroscopy, what you get, for example, with long slit spectroscopy, you get spectrum of the continuum, which is usually like a bright line across your detector with superimposed dark bands or brighter bands showing you the absorption or emission lines. To find out the different wavelengths at which each of those bands is, you go through a certain process which is called calibration. So for the Fabry-Perot, what you get is very different from traditional long slit spectroscopy. You get, like I said, an image, but that image is actually like a spherical surface, cut out of a spherical surface where the wavelength varies with the radius. So the wavelength you have at each point in your image is different, and also the wavelength you have for each step of your spectral axis is different.
Oh, this is getting complicated now.
So, yes. Now, what you get actually, just imagine you have, the birthday cones that we wear on the heads for kids' birthdays?
Oh, like the party hat.
Yes, the party hats. So imagine the party hats, and you've stacked several of them on top of each other. So what you have is conical surfaces of constant wavelength.
Okay.
And the software to unravel these and to help determine the wavelengths at different points in the images. That's what I'm working on, as well as software to help observers reduce data, because generally observers, and when you have to deal with a complex data set, you're not likely going to put in a proposal to get observations, because like, why should I suffer with the data?
It's like a double-edged sword. You get the data, but then you have to deal with it, and it's really hard to deal with it.
Yes. So we want to give our observers ready to use data. So besides calibration, we are also writing data reduction software so that the proposers can feel encouraged that they're going to get a ready to use piece of data. So that's my work, writing the software.
Oh, so you're going to make everyone's life much easier by producing. Yeah. Wonderful.
Apparently, well, that's what we hope. That's what we hope. Yeah, so that's what I do, and also offering PI support, and there's a lot in my job description, but that's the core part.
Oh my goodness. Okay, you must be so busy. Wow, this is incredible.
I think it's more fun than busy.
Oh, good. So you really enjoy your job.
If you enjoy what you're doing, then
yeah.
yes.
Oh, that makes it easier. Wonderful. Sounds like you have to do a lot of programming. How do you feel about that? Do you enjoy programming? How did you learn to do this?
Oh, yes, I do enjoy programming. So I learned to do programming during NASP, actually. That's one of the first things that they taught us when it came to NASP. It was like a crash course, but when something is interesting, you quickly pick interest and like, I would like to learn more about this. So I learned a bit more during my master's. It so happens that the projects I did for my master's and my PhD were quite code intensive, and I'm so glad to actually have had supervisors that were coders, and it was a big deal to them, and they made sure they taught me. And
oh, that's really good.
yeah. One of the pain points was them insisting you have to write every software that you need to use during this PhD. And they're like, you are not going to use anything that you have not written. If you use standard software, first find out what is the code behind it.
Whoa, that's amazing. But that must have done you so well for the future.
Yeah, it helped me to realize how much fun it is to learn something new all the time. And for me, what I found very interesting when I was introduced to coding was you can actually tell a computer what you want it to do, and it will do it.
Yeah, I agree.
That I remember the very first week when we were taught programming by the NASP program. That was my reaction, and I was sold out.
Oh, that's fantastic. Yeah, I actually found that I was so scared of programming. I tried to avoid it for as long as possible, which was a big mistake because it's the most useful skill and actually really fun.
It is. It's so much fun. Yeah, so I get to do quite a lot of it, and the fact that I'm learning something new all the time. That's the cool thing about programming, is that you don't have to have figured it out before you start. You find a challenge, and then the challenge challenges you to find a solution.
And you basically learn another language just to solve the solution.
Yes.
So I'm interested.
Yeah, it's quite interesting.
I only know how to program with Python. Do you use that a lot, or do you use different languages?
The salt standard pipeline is written in Python. So even now, the programs that I'm writing, they are in Python. And it's the language that I've mostly used most of the time. But along the way, I've always found myself having to learn something about different languages to get past a certain problem, So I found... At different times, I found myself coding in a language that I would probably never code in again, but I had to write something.
Fantastic. Oh, so skilled. I'm so impressed. So you mentioned that the Fabry-Perot mode has been not working for quite a long time, and now thanks to the work of you and others, it's being recommissioned. When do you think that will happen?
Yes, actually, there's good news coming up soon, and we hope that before the end of this year, we will be in the middle of recommissioning. As I mentioned, the plates were being refurbished and getting new housings and improvements, new and improved
Yeah.
type of thing. Um,
Upgraded.
so we hope to very soon receive them back from the contracted company and start the measurements, laboratory measurements, sky measurements, and science commissioning.
Very cool.
Yeah,
Exciting times
so
ahead.
hopefully very soon, yes. Exciting
Nice.
times ahead.
Fantastic. And I think I'll have to let you get back to all of your very important, very busy work now. But do you have any final messages for listeners before we go?
Yes, I do have something to say to the listeners, and I think my heart mostly goes out to students, especially those that are starting out, maybe university or high school. One thing that I found that used to bother me a bit when I was in school, both high school and university, and I think it's my dad that helped me to see it because he is a scientist himself, that there's no need to fear science. It's actually not a difficult, inaccessible thing. Science is actually fun. But if you fear it before you approach it, then it will feel difficult to you. That's something I always like to tell students and people generally. Science is fun and it's yours for the taking. I don't know how to emphasize it anymore, but I like to say that quite a lot to the students. If you can just engage with it. Like there's a famous celebrity, I don't know her name, but she likes to say that clarity comes with engagement.
Yes. Oh,
Yeah.
that's wonderful.
Well, maybe also just to put Luganda, my language, on the Cosmic Savannah podcast.
Yes, please do.
although although I'm a mixture of so many things in Uganda, but I'll just say one thing. Thank you very much for having me here. Webale nnyo okumpita okubeerako naawe.
Yay! It was an absolute pleasure to have you here, and thank you so much for your time, Liz.
Thank you so much. It was so amazing speaking with you. I am so glad to be here. Thank you.
You're very welcome. Thanks again. Bye.
Bye. Thank you.
Thanks for the interview. It was really great to hear. And I was actually in Sutherland last week when Liz had her first observing run. We were there, as I mentioned earlier, with the Parliamentary Portfolio Committee, so a bunch of members of the South African Parliament who were visiting the site and seeing what we're up to. And Liz was one of two ladies, the astronomer and the operator, running the Sol telescope that night. So two African ladies, young, trained in South Africa and operating the largest telescope in the Southern Hemisphere. So it was very cool.
Oh, that is so cool.
Right?
That is epic. Oh my gosh, that's so cool. And of course, it's an honor and a pleasure to have Liz on this episode to help us celebrate the Women and Girls in Astronomy project. But just to state clearly that we definitely don't need any excuse to have fantastic women on this podcast, but it is awesome that we could have Liz.
Yeah, and I mean, there's more and more. I think that we've probably talked about it before, but the observatory 20 years ago, I think, had one woman astronomer out of the 20, and now I think we're on 12 or something. So we're greater than 50% female astronomers at the observatory here. And I mean, it's wonderful. It's wonderful, the change that's happened in just 20 years.
Yeah, and we've got a high fraction of women lecturers now at UCT, at the Department of Astronomy, which is great.
To which you're contributing, obviously.
Yeah, well, yes. Now I am.
Yeah, and just great to hear Liz getting involved with SALT. I mean, even if it's not necessarily her job, just the passion to want to get involved and sort of understand what's going on and experience it. It's an incredible thing to see SALT and being able to spin around this 4-story telescope and get some awesome observations and following up near-Earth asteroids too, which is really cool.
Yeah, that must have been so awesome.
And not easy, I'm sure, moving that telescope, to track an object which is generally moving across the sky quite quickly.
Yeah, it's a hefty thing.
It sure is.
Still haven't seen it, but one day,
Well, I mean,
one day.
now you're a lecturer at UCT, but you're still remotely operating from Australia. But when you're back here,
Yes, still in Australia, but, pending visas, I will make my way back to South Africa, fingers crossed.
you've got to get your students to SALT too. So
Yeah, I guess I do. That'll be fun.
field trip, you'll be the best lecturer ever.
Well, the students actually do usually go on a field trip to Sutherland. Not since COVID hit, but yeah, hopefully we get to go back there again soon. So I think that's it for today, and thanks very much for listening, and we hope you'll join us again for the next episode of The Cosmic Savannah.
As always, you can visit our website, thecosmicsavannah.com, where we'll have the transcript, links, pictures, and other stuff related to today's episode.
You can follow us on Twitter, Facebook, and Instagram at Cosmic Savannah. That's Savannah spelled Savannah. And you can also find us on YouTube, where audio-only episodes are uploaded with closed captions, which are great because they can be auto-translated into many different languages, including Afrikaans, isiXhosa, and Zulu. Special thanks today to Dr Elizabeth Naluminsa for speaking with us.
Thanks to our social media manager, Sumari Hatting, and our audio editor, Jacob Fahn. Also to Mark Allnut for music production, Mihal Werchek for photography, Carl Jones for astrophotography, and Susie Karras for graphic design.
We gratefully acknowledge support from the South African National Research Foundation, the South African Agency for Science and Technology Advancement, the South African Astronomical Observatory, and the University of Cape Town Astronomy Department.
You can subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts, and we'd really appreciate it if you could rate and review us, or recommend us to a friend.
And we'll speak to you next time on The Cosmic Savannah.
Yeah, the International Astronomical Union is running a Women in Astronomy Month. Is it a month?
I think it's like a couple of weeks. It's between the... Oh, are we recording or... Are you just
Yeah, we're
asking
recording.
me?
Do it.
Oh.
We're recording.
Oh, there's one for the
Conversational.
blooper.
Conversational.